Every atom in your body was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of it came from stellar furnaces that burned billions of years ago. Tonight, we'll trace the complete journey of stars, from their birth in cold clouds to the explosive deaths that scattered these elements across space. We'll move through billions of years of stellar evolution, exploring the physics that transforms hydrogen into everything else, the timescales that dwarf human comprehension, and the different paths stars take depending on how massive they are when they form. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Get comfortable as we begin with the places where stars are born. Stars form in regions of space filled with gas and dust. These regions, called molecular clouds, are among the coldest places in the galaxy. Temperatures here typically range from 10 to 20 Kelvin, just a few degrees above absolute zero. The material is primarily hydrogen, with helium accounting for most of the remainder, and trace amounts of heavier elements mixed throughout. A molecular cloud can contain enough material to form thousands of stars. The total mass might reach tens or hundreds of thousands of times the mass of our Sun. These clouds span distances measured in light years, sometimes extending across 50 or 100 light years of space. Despite containing so much material, they remain diffuse by terrestrial standards. The density is far lower than the best vacuum achievable in laboratories on Earth. Within these vast structures, gravity works continuously to pull material together. The process happens slowly, over timescales of millions of years. Small variations in density create regions where matter collects more readily. These denser pockets attract additional material from their surroundings, gradually growing in mass and gravitational influence. The temperature of the gas plays an important role in determining whether a region will collapse. Warmer gas has particles moving faster, creating pressure that resists gravitational compression. Colder gas offers less resistance, allowing gravity to dominate more easily. The molecular clouds where stars form are cold enough that gravity can overcome the internal pressure, at least in localized regions. Disturbances can trigger the collapse of these dense regions. A shock wave from a nearby supernova explosion might compress part of a cloud, initiating the formation of new stars. The passage of the cloud through a spiral arm of the galaxy can produce similar compression. Even the collision of two molecular clouds can create conditions favorable for star formation. As material falls inward under gravity's influence, the center of the collapsing region grows denser and hotter. The particles collide more frequently as they crowd together, converting gravitational potential energy into thermal energy. This process continues over hundreds of thousands of years, gradually building up a central concentration of matter. The surrounding gas and dust don't simply fall straight toward the center. Conservation of angular momentum causes the infalling material to form a rotating disk around the growing core. This disk plays an important role in the subsequent evolution of the system, both in feeding additional material to the forming star and in potentially creating planets. The rotation introduces complexity to the collapse. Material in the disk orbits the center, held in balance between gravitational attraction and centrifugal effects. Some of this material will eventually spiral inward and join the central object, while other portions may remain in orbit or be expelled from the system entirely. Magnetic fields thread through the cloud, coupling to the ionized fraction of the gas. As the cloud collapses, these fields get drawn inward and amplified. The magnetic forces can slow the rotation of the central core and channel material along field lines, creating jets that shoot out perpendicular to the disk. Not all molecular clouds are actively forming stars at any given time. Some remain stable for long periods, neither collapsing nor dispersing. The balance between gravity, internal pressure, magnetic support, and turbulent motions determines whether a particular cloud or region within a cloud will begin forming stars. Turbulence within molecular clouds creates a complex internal structure. Supersonic flows generate shocks and compressions that produce filaments and clumps within the larger cloud. These smaller structures can become sites of star formation if conditions are appropriate. The composition of the cloud material reflects the history of earlier stellar generations. When the universe was young, clouds contained only hydrogen and helium, the elements formed in the Big Bang. Stars that formed from this primordial material processed these light elements into heavier ones through nuclear fusion. When those early stars ended their lives, they returned enriched material to space, gradually building up the abundance of elements heavier than helium. Modern molecular clouds contain small but significant amounts of these heavier elements. Carbon, oxygen, nitrogen, silicon, and iron exist in trace quantities. These elements allow molecules to form, and those molecules can radiate energy effectively, helping the cloud to cool. Dust grains composed of silicates and carbon compounds provide surfaces where molecules can assemble. The dust within clouds plays multiple roles. It absorbs starlight from background sources, making the clouds appear dark against the backdrop of the galaxy. This absorption heats the dust slightly, causing it to emit radiation at infrared wavelengths. The dust also shields the interior of the cloud from ultraviolet radiation that would otherwise heat the gas and inhibit collapse. Observations of molecular clouds reveal a hierarchy of structures. The larger scales show the overall cloud, which might be part of a still larger complex. Within the cloud, smaller clumps stand out, each potentially capable of forming a cluster of stars. Within those clumps, denser cores mark sites where individual stars or small groups are beginning to form. The process of star formation is inefficient in the sense that not all the material in a cloud ends up in stars. Stellar winds and radiation from the newly forming stars push on the surrounding gas, dispersing it before it can collapse further. Supernovae from massive stars can blow away much of the remaining material. The result is that only a small fraction of a cloud's mass, perhaps a few percent, typically converts into stars before the cloud dissipates. This inefficiency has important consequences. It means that star formation is a self-limiting process. As stars form, they destroy the conditions needed for further formation. It also means that the material returned to space by dying stars gets recycled repeatedly, participating in multiple cycles of cloud formation, star birth, stellar evolution, and return to the interstellar medium. The collapsing core at the center of a forming star system passes through several stages before becoming a true star. These stages together constitute the protostellar phase, a period lasting roughly 500,000 years for an object destined to become similar to our Sun. More massive objects pass through this phase more quickly, while less massive ones take longer. At first, the collapsing core is deeply embedded in its natal cloud. The dense surrounding material absorbs any visible light the core might emit, re-radiating the energy at infrared wavelengths. Observations at these longer wavelengths can penetrate the obscuring dust and reveal the forming star within. As material continues to fall onto the growing protostar, its central temperature and density increase. The pressure from the weight of overlying material compresses the core. However, the temperature remains far below what's needed for nuclear fusion. The object shines by converting gravitational energy into heat as material falls onto its surface. During this phase, the protostar is larger and more luminous than it will be once it reaches the main sequence. The additional luminosity comes entirely from the release of gravitational potential energy. The surface temperature is relatively cool, typically a few thousand Kelvin, giving the object a reddish color. The accretion disk surrounding the protostar provides a reservoir of material that continues to feed the central object. Friction within the disk causes it to heat up, and the inner regions can become quite hot. The disk emits its own radiation, often producing a distinctive infrared excess that helps identify these systems. Not all the material in the disk falls onto the star. Powerful outflows develop, driven by the interaction between the magnetic field and the rotating disk. These outflows take the form of bipolar jets, streams of gas shooting away from the star along the rotation axis. The jets can extend for light years, ploughing into the surrounding cloud and creating shock waves. Where these jets impact the ambient gas, they create glowing regions called Herbig-Haro objects. These are sites of energetic collisions between the jet material and the cloud. The shocks heat the gas, causing it to emit light. The appearance of Herbig-Haro objects changes over human timescales as the jets push farther into the cloud and as variations in the mass loss rate create density fluctuations in the outflow. The outflows carry away angular momentum from the star disk system. This is important because conservation of angular momentum would otherwise cause the star to spin faster and faster as it contracts. By removing angular momentum through winds and jets, the system avoids this problem, allowing material to continue accreting onto the central star. Eventually, the infall of material from the surrounding envelope slows and stops. The protostar has gathered most of the material that gravity can deliver. The remaining gas and dust in the disk may form planets, or it may be blown away by radiation pressure and stellar winds. The central object is now a pre-main sequence star. Pre-main sequence stars are visible in optical light because they are no longer buried in dense cocoons of dust. They are still contracting under gravity, still converting gravitational potential energy into luminosity. The contraction proceeds on a timescale called the Kelvin-Helmholtz time, which depends on the star's mass and luminosity. For a solar mass star, the pre-main sequence phase lasts about 30 million years. During this time, the star slowly shrinks and its surface temperature increases. The path it follows on a plot of luminosity versus temperature is called the Hayashi track in the earliest phases and the Henye track as it approaches the main sequence. Stars in this phase are often variable, exhibiting irregular fluctuations in brightness. These variations arise from several causes. The star structure is not yet in equilibrium, leading to instabilities. Accretion from a residual disk can be unsteady. Spots on the stellar surface, similar to the sunspots but covering larger fractions of the surface, can cause brightness variations as the star rotates. Young stars also exhibit strong magnetic activity. The magnetic field, generated by dynamo processes in the stellar interior, organizes into active regions where loops of field lines connect the surface to the corona. These regions are sites of flares and other energetic events that release bursts of radiation across the electromagnetic spectrum. As the pre-main sequence star contracts, its core temperature gradually increases. Gravitational compression continues to convert potential energy into thermal energy, heating the interior. When the central temperature reaches about 1 million Kelvin, deuterium fusion begins. Deuterium is a rare isotope of hydrogen with 1 proton and 1 neutron in its nucleus, and it fuses at lower temperatures than ordinary hydrogen. The fusion of deuterium provides a temporary source of energy that slows the contraction. However, deuterium is so scarce that it's quickly exhausted, typically within 1 million years or less. Once the deuterium is gone, the contraction resumes, and the core temperature continues to rise. For stars somewhat more massive than the Sun, lithium fusion occurs next, again providing a brief pause in the contraction. But like deuterium, lithium is present in only trace amounts and is soon depleted. The contraction continues until the core reaches the temperature and density required for sustained hydrogen fusion. The onset of hydrogen fusion marks the arrival on the main sequence. This is the point at which the star finally generates enough energy from nuclear reactions to balance the energy it radiates from its surface. The contraction stops, and the star settles into a stable configuration that it will maintain for most of its life. The main sequence is not a point, but a phase lasting billions of years. For the remainder of this discussion, we'll explore what happens during this long, stable period and what comes after. A star on the main sequence is in hydrostatic equilibrium. The inward pull of gravity is balanced at every point by the outward push of pressure. This balance is stable, meaning that if the star is slightly compressed, it responds by generating more energy, which increases the pressure and restores the balance. If the star expands slightly, energy generation decreases, pressure drops, and gravity brings it back. The energy that maintains this balance comes from nuclear fusion in the core. At temperatures above 10 million Kelvin, hydrogen nuclei can overcome their electrical repulsion and merge to form helium. This process releases energy because the helium nucleus has slightly less mass than the 4 hydrogen nuclei that went into making it. The missing mass converts to energy according to Einstein's equation, relating mass and energy. There are 2 main pathways for hydrogen fusion, both ultimately converting 4 protons into 1 helium nucleus, 2 positrons and 2 neutrinos, along with the release of energy. The proton-proton chain dominates in stars like the Sun and less massive stars. The CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts, dominates in more massive stars where core temperatures are higher. The rate of energy generation depends sensitively on temperature. Small increases in core temperature lead to large increases in the fusion rate. This sensitivity is what makes the hydrostatic equilibrium stable. If the core contracts and heats up, fusion rates surge, generating more energy and increasing pressure, which reverses the contraction. Energy released in the core must make its way to the surface to be radiated into space. In the deep interior, the material is so dense and hot that radiation cannot travel far before being absorbed and re-emitted. Energy diffuses slowly outward through this radiative zone, with photons zigzagging through countless interactions on their journey from core to surface. In the outer layers of the star, energy transport can switch to convection. When the temperature gradient becomes steep enough, buoyancy drives turbulent motions. Hot material rises, cools by radiating energy at the surface, and then sinks back down to be reheated. This convective zone extends from the surface down to about 30% of the radius in stars like the Sun. More massive stars have different internal structures. In stars several times the mass of the Sun, the core is convective because the CNO cycle's strong temperature dependence makes the core unstable to convection. The outer layers are radiative. This is the reverse of the Sun's structure. The least massive stars, the red dwarfs, are convective throughout. Their low core temperatures mean fusion rates are slow, and the structure is fully mixed by convection. This has interesting consequences for their evolution, as we'll see later. Stars spend the longest portion of their lives on the main sequence. The duration depends on mass. Massive stars burn through their hydrogen quickly, while low-mass stars proceed more slowly. The relationship is steep. A star 10 times the Sun's mass lives only about 20 million years on the main sequence. A star half the Sun's mass will remain there for more than 50 billion years, longer than the current age of the universe. The reason for this counterintuitive relationship is that luminosity increases rapidly with mass. A star 10 times the Sun's mass is roughly 10,000 times more luminous. It has more fuel, but it burns through that fuel at a much higher rate, leading to a shorter lifespan. Our Sun is about halfway through its main sequence lifetime. It formed roughly 4.5 billion years ago and will remain on the main sequence for another 5 billion years or so. Over this time, it has gradually increased in luminosity by about 30%. This increase occurs because the fusion of hydrogen into helium slowly changes the composition of the core. As helium accumulates, the mean molecular weight of the core material increases. For a given pressure, higher mean molecular weight means higher density. The core therefore contracts slightly, heating up and increasing the fusion rate. This causes the star to become more luminous over time, a gradual evolution that continues throughout the main sequence phase. The accumulation of helium in the core is the seed of the star's eventual departure from the main sequence. Helium produced by fusion settles toward the center because it's denser than hydrogen. The core becomes increasingly helium-rich, while the surrounding envelope remains mostly hydrogen. This stratification will have important consequences when the hydrogen in the core is exhausted. Main sequence stars exhibit a range of masses, from about 8% of the Sun's mass up to perhaps 100 solar masses or more. This range encompasses a huge variety of properties. The least massive stars are cool, red, and dim, with surface temperatures around 3000 Kelvin and luminosities a few thousandths that of the Sun. The most massive are hot, blue, and extraordinarily bright, with surface temperatures exceeding 30,000 Kelvin and luminosities 1,000,000 times the Sun's or greater. The mass-luminosity relationship means that massive stars dominate the light output of any stellar population, even though they are rare. In a typical region of star formation, most stars by number are low-mass red dwarfs, but most of the light comes from a few massive stars. Massive stars also have powerful stellar winds. Radiation pressure acting on atoms in the atmosphere drives material away from the star. These winds can carry away a significant fraction of the star's mass over its lifetime, particularly for the most massive objects. The lost material enriches the surrounding interstellar medium with processed elements. The main sequence phase ends when hydrogen in the core is exhausted. The core now consists primarily of helium, no longer undergoing fusion. The lack of energy generation means the core can no longer support itself against gravity, and it begins to contract. This contraction marks the beginning of the star's evolution off the main sequence. When a star like the Sun exhausts the hydrogen in its core, the immediate result is that the core begins to contract. This contraction releases gravitational energy, heating the core and the layers immediately surrounding it. The hydrogen in a shell around the core reaches fusion temperatures and begins to burn. This shell-burning phase marks the beginning of the star's transformation into a red giant. The energy output from the hydrogen-burning shell exceeds what the star was producing on the main sequence. The increased energy causes the outer layers to expand substantially. As the envelope expands, its surface area increases, and even though the total energy output is higher, the energy per unit area decreases. The surface cools, and the star takes on a reddish color. The expansion continues over millions of years. A star that was similar in size to the Sun can grow to a radius of tens or even hundreds of times larger. The outer layers become so diffuse that their density is lower than the best laboratory vacuums on Earth. The star has become a red giant. Despite the expansion and cooling of the envelope, the core continues to contract and heat up. The contraction is inevitable because the helium core produces no energy of its own and must compress to support the weight of the overlying layers. As the core shrinks, its density increases significantly. In stars similar to or less massive than the Sun, the core eventually reaches a state called electron degeneracy. In this state, the electrons resist further compression, not through ordinary thermal pressure, but through a quantum mechanical effect. The Pauli exclusion principle forbids electrons from occupying the same quantum state, and when they are packed tightly enough, this exclusion creates a pressure that doesn't depend on temperature. The degenerate core continues to heat up as it contracts, but the pressure remains roughly constant because it no longer depends on temperature. This creates an unstable situation. When the core temperature reaches about 100 million Kelvin, helium fusion ignites suddenly in what's called the helium flash. The helium flash is a runaway event. The fusion of helium produces energy, which normally would heat the gas, increase its pressure, and cause it to expand, thereby regulating the reaction. But in a degenerate core, increased temperature doesn't increase pressure, so there's no automatic stabilizing feedback. The fusion rate surges, heating the core even more, and the process accelerates. The helium flash seems striking, but it's not visible from outside the star because it happens deep in the interior. The energy released goes primarily into breaking the degeneracy by heating the core enough that thermal pressure becomes important again. Once degeneracy is lifted, normal regulation resumes, and helium fusion proceeds in a controlled manner. After the helium flash, the star settles into a new equilibrium. Helium fuses into carbon in the core, while hydrogen continues to fuse in a shell around the core. The star shrinks somewhat from its red giant dimensions and becomes less luminous. This phase is called the horizontal branch in certain populations of stars. Helium fusion proceeds through the triple alpha process. Two helium nuclei collide to form beryllium-8, which is highly unstable and normally decays immediately. But if a third helium nucleus collides with the beryllium-8 before it decays, the result is a stable carbon-12 nucleus. A carbon-12 nucleus can capture another helium nucleus to form oxygen-16. The core now contains a mixture of helium, carbon, and oxygen. The exact proportions depend on various factors, including the density and temperature of the core. As helium fusion continues, the core gradually transforms into carbon and oxygen, just as the hydrogen core earlier transformed into helium. Helium burns faster than hydrogen did because the core temperature must be higher for helium fusion to occur. A star that spent billions of years fusing hydrogen in the core will exhaust its helium in only tens or hundreds of millions of years. The phase is much shorter. When the helium in the core is exhausted, the core begins to contract again. The star is left with a carbon-oxygen core, surrounded by a shell where helium is fusing, surrounded by another shell where hydrogen is fusing, all wrapped in a vast envelope of mostly hydrogen. The carbon-oxygen core contracts and heats, but for stars in the mass range we're discussing, roughly from half a solar mass to about 8 solar masses, the core never gets hot enough for carbon fusion. The maximum temperature the core can reach, even with continued contraction, is below the threshold needed to fuse carbon. Instead, the core contracts until electron degeneracy sets in again. It becomes a degenerate carbon-oxygen core, similar to the degenerate helium core that preceded the helium flash. But there will be no carbon flash. The core simply contracts to the point where degeneracy pressure halts further collapse, and there it stops, supported by quantum mechanics. Meanwhile, the shells continue to burn. The energy they produce causes the envelope to expand even more substantially than before. The star ascends what's called the asymptotic giant branch. It becomes extremely large and luminous, with a cool surface giving it a deep red color. Stars on the asymptotic giant branch are unstable. The shell burning proceeds in pulses. The helium shell, squeezed between the inert core and the hydrogen shell, builds up helium from the hydrogen burning above it. Periodically, conditions become favorable for a brief burst of helium fusion in the shell, a thermal pulse. These pulses temporarily disrupt the structure, causing the envelope to expand and cool. Between thermal pulses, the hydrogen shell returns to dominance, and the cycle repeats. The thermal pulses occur on timescales of tens of thousands to hundreds of thousands of years. Each pulse can temporarily increase the star's luminosity by a large factor. During this phase, the star develops strong convection in the envelope. Deep convective currents can reach down to regions where nuclear processing has occurred, dredging up fusion products to the surface. This mixing changes the surface composition, and observations of such enrichment provide clues about the star's internal structure and history. The outer layers of an asymptotic giant branch star are loosely bound. The effective gravity at the surface is weak because of the star's enormous radius. Stellar winds become increasingly strong, driven by radiation pressure on dust grains that form in the cool atmosphere. These winds carry away the outer envelope, slowly eroding the star. The mass loss rate can become substantial, reaching a 10,000th of a solar mass per year or more. Over time, the wind removes most of the hydrogen envelope, exposing the deeper layers. The rate accelerates as the envelope thins, because the same luminosity drives the wind, but there's less mass to push away. Eventually, the hydrogen envelope is entirely removed, leaving the hot core exposed. The core, no longer buried under layers of cool gas, can radiate its thermal energy directly to space. Its surface temperature is high, often exceeding 100,000 Kelvin, and its ultraviolet radiation illuminates the expelled gas around it. This expelled gas forms a planetary nebula, so named because early telescopes showed these objects as round, planet-like disks. The nebula is the former envelope of the star, now spread over a region a light-year or more across. The ultraviolet light from the central star ionizes the gas, causing it to glow with characteristic colors. A white dwarf is the remnant core of a low or intermediate mass star. It's composed primarily of carbon and oxygen, though some may have other compositions depending on the details of their evolution. The mass is typically around half to one solar mass, packed into a volume about the size of Earth. The density of a white dwarf is extreme by everyday standards. A teaspoon of white dwarf material would weigh several tons. At such densities, matter behaves in ways governed by quantum mechanics. Electrons are packed so tightly that degeneracy pressure dominates over thermal pressure. This degeneracy pressure supports the white dwarf against further collapse. Unlike ordinary pressure, degeneracy pressure doesn't depend on temperature. The white dwarf doesn't need an internal heat source to maintain its structure. It can cool indefinitely while remaining stable. When first exposed, a white dwarf is extremely hot, with surface temperatures that can exceed 100,000 Kelvin. The high temperature is a result of the core contraction that preceded the loss of the envelope. The white dwarf initially glows intensely blue-white, hence the name. However, the white dwarf has no energy source. It generates no fusion reactions, and gravitational contraction has ceased because degeneracy pressure prevents further collapse. The only energy available is the thermal energy stored in the ions that make up the bulk of the matter. The white dwarf cools by radiating this stored heat into space. The cooling proceeds slowly. A white dwarf's high density and the efficiency of degeneracy pressure mean it can remain luminous for billions of years. The cooling rate depends on the mass and composition, but typical white dwarfs take 10 billion years or more to fade to very low luminosities. As a white dwarf cools, its surface temperature decreases and its color shifts from blue-white to yellow to red. Eventually, after cooling for longer than the current age of the universe, it would become a black dwarf, a cold, dark object radiating negligibly. No black dwarfs exist yet because the universe is not old enough for even the oldest white dwarfs to have cooled to this state. White dwarfs represent the final state for the vast majority of stars. Any star born with a mass below about 8 solar masses will end as a white dwarf. This includes the Sun and most stars in the galaxy. The maximum mass a white dwarf can have is about 1.4 solar masses, a limit called the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the object, and further collapse occurs. Since stars more massive than 8 solar masses leave remnants exceeding this limit, they cannot form stable white dwarfs. They follow a different path, which we'll explore shortly. White dwarfs in binary systems can sometimes accrete material from a companion star. If the companion is a red giant with a distended envelope, material can flow from the giant onto the white dwarf. This accretion can lead to interesting phenomena. The infalling material forms an accretion disk around the white dwarf, gradually spiraling inward. When hydrogen-rich material accumulates on the white dwarf's surface, the base of this layer can reach fusion temperatures. Eventually, the accumulated hydrogen ignites in a runaway thermonuclear explosion on the surface, an event called a nova. A nova causes the star to brighten suddenly, sometimes by 10 magnitudes or more, as the surface layers are ejected. The white dwarf itself survives the explosion, and after the ejected material disperses, accretion can resume. The process can repeat, with some systems undergoing recurrent novae every few decades. In rare cases, if a white dwarf accretes enough material to approach the Chandrasekhar limit, or if 2 white dwarfs merge, the result can be a catastrophic collapse followed by a thermonuclear explosion that destroys the star entirely. This is a Type 1a supernova, and we'll discuss these events later. Most white dwarfs, however, lead quiet existences. They cool slowly in isolation, contributing little to the dynamics of the galaxy. They represent endpoints of stellar evolution, compressed cores enriched in carbon and oxygen, no longer capable of fusion, supported by quantum mechanics, gradually fading over timescales comparable to the age of the universe. The fate of low-mass stars, those less massive than the Sun, is similar, but stretched over even longer timescales. A star with half the Sun's mass will spend more than 50 billion years on the main sequence. When it eventually exhausts its core hydrogen, it will evolve into a red giant, undergo helium fusion, and ultimately shed its envelope to become a white dwarf. The least massive stars, the red dwarfs below about a third of a solar mass, are fully convective. The mixing brings fresh hydrogen from the outer layers down to the core, allowing these stars to fuse all their hydrogen, not just the core hydrogen. This extends their lifetime substantially. The smallest red dwarfs could in principle burn for trillions of years. No red dwarf has yet exhausted its fuel, because the universe is only about 14 billion years old. The evolution of the lowest mass stars is a matter of theoretical prediction rather than observation. Models suggest they will gradually contract and heat as they age, eventually becoming blue dwarfs and then white dwarfs without ever becoming red giants. The ultimate fate of all these stars is to become cold, inert remnants. The timescale for this cooling exceeds current estimates of the universe's age many times over. In this sense, stellar evolution is an incomplete story. We observe stars at various stages, but the true endpoints lie far in the future, beyond the reach of current observation. Stars born with more than 8 solar masses follow a different evolutionary path. Their greater mass allows their cores to reach higher temperatures and densities, enabling fusion reactions beyond helium burning. These stars produce the full range of elements up to iron and are responsible for the chemical enrichment of the galaxy. A massive star's main sequence lifetime is brief by stellar standards, measured in millions rather than billions of years. A star 20 times the Sun's mass might spend only 10 million years fusing hydrogen in its core. The pace of evolution accelerates at each subsequent stage. When core hydrogen is exhausted, the star expands into a supergiant. The evolution is qualitatively similar to lower mass stars in that hydrogen shell burning begins, and the envelope expands and cools. However, the timescales are much shorter, and the temperatures reached in the core are much higher. The core contracts and heats until helium fusion begins. For massive stars, this ignition occurs without a helium flash, because the core is not degenerate. The high temperatures and the mass of the core mean that thermal pressure dominates, and helium fusion proceeds smoothly and stably. Helium burns in the core, producing carbon and oxygen. This phase lasts perhaps 1 million years for a 20 solar mass star. When helium is exhausted, the core contracts again, and helium fusion continues in a shell. The carbon-oxygen core heats up as it contracts. For massive stars, the core eventually reaches the temperatures needed for carbon fusion, around 600 million Kelvin. Carbon nuclei fuse to produce neon, sodium, and magnesium, along with releasing energy. Carbon burning is faster still. The core might burn carbon for only a few thousand years. The progression continues. When carbon is exhausted, the core contracts and carbon shell burning begins. The core heats until neon fusion starts. Neon burning occurs at temperatures around 1.5 billion Kelvin. The process disintegrates neon nuclei into oxygen and helium, and the helium then fuses with other nuclei to build heavier elements like magnesium. This stage lasts about a year. After neon is exhausted, oxygen burning begins at about 2 billion Kelvin. Oxygen fusion produces silicon, sulfur, and other elements in that mass range. Oxygen burning proceeds for roughly half a year in a 20 solar mass star. Finally, silicon burning begins at temperatures around 3 billion Kelvin. Silicon nuclei break apart and recombine in a complex network of reactions that gradually build elements up to iron, cobalt, and nickel. This final stage lasts only about 1 day. The structure of the star at this point resembles an onion with multiple layers. At the center is an iron core. Surrounding it are shells where silicon is burning, then oxygen, neon, carbon, helium, and hydrogen, with the outer envelope of mostly unprocessed hydrogen. Each burning stage releases less energy than the previous one because the binding energy per nucleon increases as you build heavier elements, but only up to iron. Iron is the most tightly bound nucleus. Fusing iron into heavier elements requires energy input rather than releasing energy. The iron core cannot generate energy through fusion. Without an energy source, the iron core is supported only by electron degeneracy pressure. As silicon burning continues in the surrounding shell, the core mass grows. When it approaches the Chandrasekhar limit of about 1.4 solar masses, degeneracy pressure can no longer support it. The core begins to collapse. The collapse is catastrophic. Within a fraction of a second, the core implodes from a size of several thousand kilometers to a radius of about 10 kilometers. The density increases to nuclear density, comparable to that inside an atomic nucleus. At such densities, protons and electrons are forced together, forming neutrons and neutrinos in a process called neutronization. The core becomes a ball of neutrons, incredibly dense, supported by neutron degeneracy pressure. This halts the collapse abruptly, and the core rebounds. The rebound sends a shock wave outward through the star. The shock initially carries a substantial fraction of the energy released in the collapse, but as it propagates through the outer layers, it loses energy. The shock stalls in the outer core, unable to continue on its own. Neutrinos produced in the neutronization of the core stream outward. Normally, neutrinos interact so weakly that they escape without hindrance, but the density in the outer core is so extreme that even neutrinos have trouble getting through. A small fraction of the neutrinos deposit their energy in the stalled shock, reviving it. The revived shock continues outward, accelerating as it moves into less dense material. When it reaches the surface, the outer layers are ejected at speeds of several % of the speed of light. The star explodes as a core collapse, supernova, also known as a Type II supernova, if hydrogen is present in the spectrum. The explosion releases an enormous amount of energy. The kinetic energy of the ejected material is about 100 times the amount the Sun will radiate over its entire 10 billion year lifetime. The neutrinos carry away even more energy, roughly 100 times the kinetic energy. The light we see from the supernova is a tiny fraction of the total energy released. The light from a supernova can briefly outshine an entire galaxy. The initial brightening takes days to weeks. The peak luminosity is reached when the expanding material becomes optically thin, allowing the energy deposited by the shock to escape. After the peak, the light curve declines, powered by the radioactive decay of nickel-56 and cobalt-56 produced in the explosion. The expanding remnant sweeps up the surrounding interstellar medium, creating a supernova remnant. The shock heats the gas to millions of degrees, causing it to emit X-rays. Over thousands of years, the remnant expands and gradually cools, eventually merging with the general interstellar medium. The material ejected contains all the elements synthesized during the star's life, from carbon and oxygen produced during helium burning, through silicon and sulfur from later stages, up to iron from the core. The explosion itself synthesizes elements heavier than iron through rapid neutron capture. The core left behind after a core collapse supernova is a neutron star. This object is one of the most extreme forms of matter in the universe. Its mass is typically between 1.4 and 2 solar masses, packed into a sphere only about 20 kilometers in diameter. The density of a neutron star is comparable to that of an atomic nucleus. Matter is compressed beyond the point where atoms can exist. Electrons and protons are forced to combine into neutrons, filling the available space. A teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars are supported by neutron degeneracy pressure, similar to how white dwarfs are supported by electron degeneracy pressure. The quantum mechanical exclusion principle prevents neutrons from occupying the same state, creating a pressure that resists further collapse. The structure of a neutron star includes several distinct layers. The outermost layer is a thin atmosphere, perhaps a centimeter thick, composed of hydrogen or helium. Below that is a solid crust several hundred meters thick. The crust consists of a lattice of neutron-rich nuclei immersed in a sea of electrons. Deeper down, the density increases to the point where nuclei merge into a continuous neutron fluid. This is the outer core, extending down several kilometers. The neutrons flow as a superfluid, meaning they have zero viscosity. Protons, present in small numbers, form a superconducting fluid. The nature of the inner core, at the very center of the neutron star, is uncertain. Densities there exceed those reproducible in any laboratory. The neutrons might break down into their constituent quarks, forming a quark-gluon plasma. Other exotic forms of matter, involving strange quarks or pion condensates, have been proposed. Observations of neutron stars provide constraints, but the inner core remains at the frontier of nuclear physics. Neutron stars are born rotating rapidly. Conservation of angular momentum means that as the core collapses from a radius of thousands of kilometers to about 10 kilometers, the rotation rate increases significantly. Newly formed neutron stars can rotate hundreds of times per second. They also possess strong magnetic fields. The magnetic field of the progenitor star is compressed along with the core, amplifying it to strengths 1 trillion times greater than Earth's magnetic field. The combination of rapid rotation and a strong magnetic field gives rise to the pulsar phenomenon. A pulsar is a rotating neutron star whose magnetic axis is misaligned with its rotation axis. Charged particles accelerated along the magnetic field lines emit beams of radiation. As the neutron star rotates, these beams sweep through space like lighthouse beams. If one of the beams points toward Earth, we detect a pulse of radiation each time the beam sweeps by. The pulse period equals the rotation period of the neutron star. For most pulsars, this is between milliseconds and seconds. The pulses are extraordinarily regular, more precise than many atomic clocks. This regularity allows precise timing measurements and has enabled tests of general relativity and the detection of gravitational waves from merging black holes. Pulsars gradually slow down over time. The emission of radiation and the acceleration of particles in the magnetosphere carry away rotational energy. The slowdown rate depends on the magnetic field strength and the rotation rate. Typical pulsars slow at a rate that increases their period by microseconds per year. Some pulsars, called millisecond pulsars, rotate hundreds of times per second and slow down much more gradually. These are thought to be old neutron stars that have been spun up by accreting material from a binary companion. The accretion transfers angular momentum, spinning the neutron star faster and partially recycling it. Neutron stars in binary systems exhibit interesting behavior. If the companion is a massive star, the system may undergo a second supernova when the companion exhausts its fuel. The two neutron stars then orbit each other. The orbit gradually decays as the system loses energy to gravitational waves, and eventually the neutron stars merge. The merger of two neutron stars is a cataclysmic event. The collision produces gravitational waves strong enough to be detected by observatories on Earth. It also produces a kilonova, a bright transient, powered by the radioactive decay of heavy elements synthesized in the merger. The collision is a major source of elements heavier than iron, including gold and platinum. Some neutron stars are magnetars, possessing magnetic fields even stronger than typical pulsars, reaching 1,000 trillion times Earth's field. These fields are so intense that they affect the structure of space itself. Magnetars undergo starquakes, sudden rearrangements of the crust driven by magnetic stresses, which release bursts of X-rays and gamma rays. Most neutron stars gradually fade from view. The emission that makes pulsars visible is powered by rotational energy, and as the neutron star slows, the emission weakens. Eventually, the pulsar turns off, becoming an inactive neutron star that emits little radiation. These silent remnants are difficult to detect, contributing to the unseen mass of the galaxy. Neutron stars represent one possible endpoint of massive star evolution. But for the most massive stars, even neutron degeneracy cannot prevent further collapse. When the remnant core exceeds about 2 to 3 solar masses, gravity overwhelms all forms of pressure, and the collapse continues to form a black hole. When the core of a collapsing massive star exceeds the maximum mass that neutron degeneracy pressure can support, no known force can halt the collapse. The core continues to shrink, and its density increases without bound. The result is a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from within a certain boundary called the event horizon. The size of the event horizon depends on the mass of the black hole. For a stellar mass black hole, the radius is about 3 kilometers per solar mass. The formation of a black hole during a supernova is difficult to observe directly because the event horizon prevents any light from escaping once it forms. Whether all massive core collapses produce visible supernovae is uncertain. Some models suggest that the most massive stars might collapse directly to black holes without a prominent explosion, a so-called failed supernova. Once formed, a black hole settles into a remarkably simple state. Classical general relativity says that a black hole is fully characterized by just 3 quantities: mass, angular momentum, and electric charge. All other information about the infalling matter is lost. This is sometimes called the no-hair theorem. Stellar mass black holes in isolation are difficult to detect because they emit no light. They can be found in binary systems if they accrete material from a companion star. The infalling material forms an accretion disk, similar to those around white dwarfs or neutron stars. However, the stronger gravity of a black hole heats the disk to higher temperatures, producing copious X-rays. The X-ray emission from these systems varies on short timescales, sometimes changing significantly in fractions of a second. This variability, combined with estimates of the compact object's mass from the orbital motion of the companion, can identify the object as a black hole rather than a neutron star. Several dozen stellar mass, Black holes have been identified in binary systems in our galaxy. The true population is likely much larger. Most black holes are probably isolated, the remnants of stars that lost their companions during the supernova explosion, or that formed from single stars. Black holes can grow by accreting material or by merging with other compact objects. The merger of two black holes releases a tremendous amount of energy in the form of gravitational waves. These ripples in spacetime were first directly detected in 2015, opening a new window onto the universe. Gravitational wave detectors have observed dozens of black hole mergers. The mergers involve black holes with masses ranging from a few solar masses to tens of solar masses. Some of these masses are higher than expected from models of single-star evolution, suggesting that black holes can grow significantly through mergers. Black holes can also exist at the centers of galaxies. These supermassive black holes have masses millions to billions of times that of the Sun. They form through different mechanisms than stellar mass black holes, possibly starting from direct collapse in the early universe, or from the merger of many smaller black holes and the accretion of vast amounts of gas. The distinction between stellar mass black holes and supermassive black holes is clear, but there may also be intermediate mass black holes with masses hundreds to thousands of solar masses. The existence of this population is uncertain, though there are some candidate detections. From the perspective of stellar evolution, black holes represent the ultimate endpoint for the most massive stars. A star born with more than about 20 solar masses will likely leave behind a black hole remnant. The exact threshold depends on uncertainties in mass loss during the star's life and the details of the supernova explosion. Black holes do not last forever, according to quantum mechanics. Stephen Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass slowly over time. The rate is inversely proportional to the mass, so stellar mass black holes evaporate extremely slowly. The timescale for a stellar mass black hole to evaporate is far longer than the current age of the universe, around 10 to the 67th power years. This is so long that the process is irrelevant for any practical consideration. By the time black holes begin to evaporate in significant numbers, the universe will be unimaginably different, with all stars long since dead and all structure dissolved. In the context of stellar evolution, black holes are endpoints. They represent the final state of massive stars, compact objects that no longer evolve in the conventional sense. They can grow through accretion or mergers, but they do not undergo the internal changes driven by nuclear fusion that characterize the lives of stars. Supernovae are among the most energetic events in the universe. They come in several types, classified by their spectra and light curves. The classification reveals different physical mechanisms underlying the explosions. Core collapse supernovae result from the collapse of massive stars, as described earlier. These are classified as type 2 if their spectra show hydrogen lines, indicating the presence of a hydrogen envelope at the time of explosion. Type IB supernovae lack hydrogen but show helium. Type IC supernovae lack both hydrogen and helium, suggesting the star lost its outer layers before exploding. The progenitors of type YB and IC supernovae are massive stars that have shed their hydrogen envelopes through stellar winds or mass transfer in a binary system. The core collapse mechanism is the same as for type 2, but the different surface compositions lead to different spectral appearances. Type 1a supernovae are different. They result from the thermonuclear explosion of a white dwarf. The progenitor is not a massive star, but rather the remnant of a low or intermediate mass star that has accreted material in a binary system. The mechanism for type 1 as supernovae is thought to involve a carbon-oxygen white dwarf accreting material from a companion. If the white dwarf's mass approaches the Chandrasekhar limit, electron degeneracy can no longer support it. The white dwarf begins to collapse, and the compression heats the carbon and oxygen. Carbon fusion ignites, but because the white dwarf is degenerate, there is no regulating feedback. The fusion rate skyrockets, heating the material even more, and the reaction runs away. Within seconds, the entire white dwarf undergoes explosive fusion, converting much of the carbon and oxygen into iron group elements and releasing enough energy to unbind the star completely. The explosion ejects all the material at high speeds, leaving no remnant behind. The light curve of a Type 1 supernova is powered by the radioactive decay of nickel-56 produced in the explosion. The peak luminosity and the decay timescale are remarkably uniform, which has made Type 1 as supernovae useful as standard candles for measuring cosmic distances. The uniformity arises because the explosion always involves a white dwarf near the Chandrasekhar limit. The physics of the explosion is similar in each case, leading to similar outcomes. Small variations exist, and understanding these variations is important for using Type 1 as supernovae as precision distance indicators. Supernovae inject energy and momentum into the interstellar medium. The expanding eject a plow into the surrounding gas, creating a supernova remnant. The shock wave heats the gas to millions of degrees, making it emit X-rays. The remnant expands over thousands of years, eventually reaching sizes of tens or hundreds of light years. Young supernova remnants are bright and structured. The Crab Nebula, the remnant of a supernova observed in the year 1054, shows intricate filaments and a pulsar at its center. The pulsar powers a nebula of relativistic particles that emits synchrotron radiation across the spectrum. Older remnants gradually fade and merge with the interstellar medium. The energy they inject stirs the gas and can trigger new rounds of star formation by compressing molecular clouds. The cycle continues. Stars form, evolve, and die, enriching the gas and driving further evolution. Supernovae are also sites of nucleosynthesis. The high temperatures and densities reached during the explosion enable the synthesis of elements that cannot be produced in stellar interiors. Rapid neutron capture, the R process, builds elements beyond iron, including uranium and thorium. The distribution of elements in the universe reflects the combined contributions of different stellar processes. Hydrogen and helium are primordial, formed in the Big Bang. Carbon, oxygen, and elements up to iron are produced in stars and dispersed by stellar, wines and supernovae. Elements heavier than iron come primarily from neutron star mergers and certain types of supernovae. The Sun's composition includes contributions from many generations of stars. The solar system formed from a molecular cloud enriched by supernovae that exploded billions of years before the Sun's birth. Earth and everything on it, including ourselves, are made of elements forged in stellar furnaces and scattered by stellar explosions. This cycle of birth, evolution, death, and rebirth is a fundamental aspect of the universe. Stars are not isolated objects with independent histories. They are part of a larger ecological system where matter is recycled, processed, and enriched over cosmic timescales. Stars are born with different compositions depending on when and where they formed. The earliest stars, forming in the first few 100 million years after the Big Bang, had compositions reflecting the primordial abundances from Big Bang nucleosynthesis. About 75% hydrogen, 25% helium, and trace amounts of lithium. These first stars, called population 3 stars, contain no elements heavier than lithium. They were likely very massive, forming from gas that could cool only through hydrogen molecular transitions because no dust or heavy elements were present to aid cooling. Their evolution was rapid, and they exploded as supernovae, enriching the surrounding gas with the first heavy elements. No population 3 star has been observed directly. If any still exist, they would be extremely faint and distant. Their existence is inferred from theoretical models and from the composition of the next generation of stars, which show trace amounts of heavy elements that must have come from earlier enrichment. Stars forming from gas enriched by earlier supernovae are called population 2 stars. These stars have low metallicities, meaning low abundances of elements heavier than helium. They are found in the oldest parts of the galaxy, the halo, the globular clusters, and the thick disk. Population 1 stars, including the Sun, have higher metallicities. They formed more recently from gas, enriched by many generations of stars. They are found in the galactic disk, particularly in the spiral arms, where star formation is ongoing. The metallicity of a star affects its evolution in several ways. Metals contribute to opacity, blocking the flow of radiation through the star and affecting its temperature structure. Metals also affect the efficiency of stellar winds. Lower metallicity stars lose less mass through winds, which influences their final states. Low metallicity stars can reach higher masses because winds are weaker. Population 3 stars may have reached hundreds of solar masses. High metallicity stars lose mass more easily, and the most massive stars may lose much of their mass before exploding, affecting the remnant they leave behind. The chemical evolution of the galaxy is a gradual process. Each generation of stars produces and disperses heavy elements, increasing the average metallicity of the gas. Over billions of years, the interstellar medium has become progressively enriched. This enrichment is not uniform. Regions of active star formation, where massive stars form and explode, become enriched faster. Gas ejected from the galaxy by supernova-driven winds can escape into intergalactic space, carrying metals with it. Conversely, gas falling onto the galaxy from the intergalactic medium is relatively pristine, diluting the metallicity. Stars in the galaxy span a wide range of ages. Some globular clusters are nearly as old as the universe, forming when the galaxy was first assembling. The Sun is middle-aged, about 4.5 billion years old. Stars are forming in the galaxy today in regions like the Orion Nebula. Each generation builds on the previous ones. The elements in Earth, in our bodies, in everything around us, were forged in stars that lived and died before the Sun formed. The oxygen we breathe came from massive stars that exploded as supernovae. The carbon in our cells was produced in red giants that shed their envelopes as planetary nebulae. The iron in our blood was synthesized in supernova explosions or in the collapsing cores of massive stars. This connection between stellar evolution and the existence of planets and life is profound. The universe started with only the lightest elements. Stars created everything else. Without stellar nucleosynthesis, there would be no rocky planets, no water, no organic molecules, no life. The study of stellar evolution is thus a study of our own origins. By understanding how stars form, live, and die, we learn about the processes that made our existence possible. The life cycle of stars is the life cycle of matter, a story of transformation and recycling that continues across the history of the cosmos. We've traced the journey of stars from their formation in cold molecular clouds to their various endpoints. Low-mass stars spend billions of years on the main sequence, evolve into red giants, and become white dwarfs that cool over trillions of years. Massive stars burn quickly through successive fusion stages, creating heavy elements and ending in supernovae that leave behind neutron stars or black holes. Throughout these cycles, stars enrich the interstellar medium with processed elements, enabling the formation of planets and the eventual emergence of life. Not all stars are solitary. About half of all stars are members of binary or multiple star systems. These systems consist of two or more stars orbiting their common center of mass. The presence of a companion can significantly alter a star's evolution. In a wide binary, the stars are separated by large distances and evolve independently. Each follows its single star evolutionary path. The main effect of the companion is gravitational, influencing the orbital motion, but not the internal structure or evolution of either star. In closer binaries, interactions become important. If the stars are close enough, they can exchange mass. This occurs when one star expands during its giant phase and fills its Roche lobe, the region around the star within which material is gravitationally bound to it. Material that crosses the boundary between the two Roche lobes can flow from one star to the other. Mass transfer changes the evolution of both stars. The donor star loses mass, which can halt its expansion or even cause it to shrink. The star receiving the mass gains fuel and can become more massive, brighter, and hotter. The transfer of material also transfers angular momentum, affecting the orbital separation and period. In some cases, mass transfer is stable, proceeding smoothly over long periods. In other cases, it is unstable, leading to rapid and substantial changes. If the donor star expands too quickly, the transfer rate can increase in a runaway fashion, potentially leading to a common envelope phase where both stars become engulfed in a shared atmosphere. The common envelope phase is brief, but crucial in the evolution of close binaries. Friction within the envelope causes the two stellar cores to spiral inward toward each other. The envelope absorbs orbital energy and can be ejected entirely, leaving behind a much tighter binary consisting of the two stellar cores. These tight binaries can evolve into exotic systems. If one star has already evolved into a white dwarf, the accretion of material from the companion can lead to novae, or, if conditions are right, a Type 1 supernova. If both stars become compact objects, the result might be a double neutron star system, or a neutron star black hole binary. Binary interactions can also affect the mass and angular momentum of the remnant left behind after a supernova. If a massive star in a binary explodes, the sudden mass loss can unbind the system, ejecting both stars at high velocities. Alternatively, the system can remain bound, but with a highly eccentric orbit. Some pulsars have been found in binary systems with white dwarfs or other neutron stars. These systems provide opportunities to test general relativity with high precision. The orbital decay due to gravitational radiation can be measured and compared to theoretical predictions, confirming the existence of gravitational waves long before their direct detection. X-ray binaries are systems where a compact object, a neutron star or black hole, accretes material from a companion star. The accretion releases gravitational potential energy, heating the infalling material to temperatures where it emits X-rays. These systems are among the brightest X-ray sources in the galaxy. In high-mass X-ray binaries, the companion is a massive star with strong stellar winds. The compact object accretes from the wind, or, if the system is close enough, through Roche, lobe overflow. In low-mass X-ray binaries, the companion is a less massive star, often a red dwarf or a subgiant, and mass transfer occurs primarily through Roche lobe overflow. Millisecond pulsars are thought to be spun up through mass transfer in a binary. The accretion transfers angular momentum to the neutron star, increasing its rotation rate. Once the mass transfer ends, the neutron star remains a rapidly rotating pulsar with a spin period of a few milliseconds. These recycled pulsars rotate faster than newly formed pulsars and have weaker magnetic fields. Some binaries undergo substantial outbursts. Symbiotic stars are systems where a white dwarf accretes from the wind of a red giant. The accretion is variable, leading to irregular brightening. Cataclysmic variables are close binaries where a white dwarf accretes from a Roche lobe-filling companion. Exhibiting outbursts due to instabilities in the accretion disk, or thermonuclear flashes on the white dwarf surface. Binary evolution is complex and depends on many factors: the initial masses of the stars, the orbital separation, the rate of mass transfer, and whether common envelope evolution occurs. Detailed modeling is required to predict outcomes, and uncertainties remain about key processes, particularly the efficiency of common envelope ejection and the response of stars to rapid mass loss. The study of binary stars enriches our understanding of stellar evolution. Many phenomena, from type 1 a supernovae to millisecond pulsars, can only occur in binary systems. The interaction between stars adds a layer of complexity and variety to the catalogue of stellar endpoints. The concept of stellar populations extends beyond the original population 1, 2, and 3 classification. Modern surveys reveal continuous variations in age and metallicity, rather than discrete populations. The history of star formation in a galaxy creates a distribution of stellar properties that reflects that history. The galactic disk contains stars of various ages and metallicities. The thin disk, where the Sun resides, contains younger stars with solar metallicity or higher. The thick disk consists of older stars with lower metallicities, formed when the galaxy was younger and less chemically enriched. The stellar halo contains the oldest stars with the lowest metallicities. Star formation history varies across galaxies. Some galaxies experienced most of their star formation early, producing old stellar populations. Others continue forming stars today, maintaining young populations. Starburst galaxies undergo intense periods of star formation, triggered by galaxy interactions or gas inflows. The initial mass function, describing the distribution of stellar masses at birth, appears remarkably universal. Observations of star-forming regions in different environments, from nearby molecular clouds to distant galaxies, show similar mass distributions. The IMF is weighted toward low-mass stars, with fewer massive stars. This explains why the galaxy contains many faint red dwarfs, but is dominated in luminosity by fewer, brighter massive stars. Variations in the IMF have been proposed in extreme environments. The very early universe, lacking heavy elements, may have formed predominantly massive stars. The cores of galaxies, with high gas pressures, might form more massive stars than typical regions. However, direct observational evidence for significant IMF variations remains limited and debated. The age metallicity relation in the solar neighborhood shows a general trend of increasing metallicity with time, as expected from ongoing chemical enrichment. However, significant scatter exists, with some old stars having relatively high metallicities and some young stars having low metallicities. This scatter reflects the inhomogeneous mixing of the interstellar medium and variations in local star formation history. Galactic archaeology uses stellar properties to reconstruct the galaxy's history by measuring ages, metallicities, and kinematics of stars. Astronomers can identify streams from disrupted satellite galaxies, trace the formation of the galactic components, and constrain models of galaxy formation and evolution. The Gaia mission has revolutionized this field by providing precise distances and motions for billions of stars. Some stars vary in brightness over time. These variable stars change due to intrinsic processes in the star itself, rather than external effects like eclipses in binary systems. Intrinsic variables include pulsating stars, eruptive stars, and cataclysmic variables. Pulsating stars expand and contract periodically. The pulsation is driven by mechanisms in the stellar envelope. In classical Cepheids, helium ionization at specific depths in the envelope acts as a valve, trapping heat when the star contracts and releasing it when the star expands. This creates a self-sustained oscillation. Cepheid variables are luminous yellow supergiants with pulsation periods ranging from a few days to months. Their importance comes from a relationship between their pulsation period and their average luminosity. More luminous Cepheids pulsate more slowly. This period luminosity relation allows Cepheids to be used as distance indicators. By measuring the period, one can infer the luminosity, and comparing this to the observed brightness gives the distance. R Lyrae stars are another class of pulsating variables. They are horizontal branch stars, less luminous than Cepheids, but still useful as standard candles, particularly in globular clusters. Their pulsation periods are shorter, typically less than a day. Long-period variables are red giants and supergiants that vary over months to years. Mirror variables, named after the star Mira, have large amplitudes, varying by several magnitudes in visible light. The variations arise from pulsations combined with the formation and dissociation of molecules in the cool atmosphere. Some stars exhibit irregular or semi-regular variations. These stars are often evolved giants with complex envelopes. Convection, pulsation, and dust formation can all contribute to variability. The star Betelgeuse, a red supergiant, varies irregularly in brightness over timescales of months to years. Eruptive variables undergo sudden increases in brightness. T Tauri stars are young pre-main sequence stars that vary due to instabilities associated with accretion and magnetic activity. Fu Orionis stars, a subset of young stars, undergo substantial outbursts lasting decades, thought to be caused by sudden increases in the rate of accretion from a disk. Cataclysmic variables involve white dwarfs in binary systems, as mentioned earlier. Their outbursts result from instabilities in the accretion process. Dwarf novae undergo outbursts every few weeks to months as material in the accretion disk becomes unstable and rapidly accretes onto the white dwarf. Studying variable stars provides information about stellar structure and evolution. The pulsation properties depend on the mass, radius, and internal structure of the star. Observations of variability can constrain models and reveal details about the star's evolutionary state. Asteroseismology extends this idea by studying oscillations with multiple periods. The Sun oscillates in millions of different modes, each corresponding to a standing wave pattern in its interior. By measuring the frequencies of these modes, researchers can probe the Sun's internal structure with precision, comparable to seismology of Earth's interior. Asteroseismology has been applied to other stars using space-based telescopes that can detect very small brightness variations. The technique has revealed information about stellar masses, radii, ages, and internal rotation profiles. It has also been used to confirm the presence of stellar cores and to test models of convection and mixing. Variable stars have been important historically. Before modern distance measurement techniques, Cepheids and RR Lyrae stars provided the primary means of measuring distances to nearby galaxies. Henrietta Leavitt's discovery of the period luminosity relation for Cepheids in the early 20th century was a key step in establishing the scale of the universe. The study of variability continues to be active. Surveys monitor millions of stars, detecting variables and transients. Time-domain astronomy, the study of how objects change over time, has become a major focus. Discoveries include new types of variables, unusual transients, and rare events like stellar collisions and tidal disruption of stars by black holes. Pulsating stars vary in brightness because their outer layers alternately expand and contract. The pulsation is driven by mechanisms operating within specific regions of the star. Understanding these mechanisms reveals how stars respond to perturbations and provides insights into stellar structure. The Kappa mechanism, operating in Cepheids and many other pulsating variables, involves opacity changes in ionization zones. At certain depths in the stellar envelope, hydrogen or helium undergoes partial ionization. When the star contracts during pulsation, this region becomes more opaque, trapping heat. The trapped heat increases pressure, driving expansion. When the star expands, the region becomes more transparent, releasing heat. Pressure drops, and gravity pulls the star inward again. This cycle repeats, sustaining the pulsation. The period of pulsation depends on the star's mean density. More compact stars pulsate faster, while more extended stars pulsate more slowly. This explains why red giants have longer pulsation periods than main sequence stars of similar temperature. The period-density relation allows astronomers to infer stellar properties from observed pulsation periods. Cepheid variables exhibit a tight period luminosity relation because their luminosity determines their radius through the Stefan-Boltzmann law, and radius determines pulsation period through the period-density relation. More luminous Cepheids are larger and pulsate more slowly. This makes them valuable distance indicators. By measuring the period, astronomers infer the luminosity, and comparing to the observed brightness gives the distance. Different types of Cepheids exist. Classical Cepheids are massive yellow supergiants burning helium in their cores. Type II Cepheids are lower mass horizontal branch stars. The two types have different period luminosity relations and must be distinguished for accurate distance measurements. Observations of their pulsation properties, light curve shapes, and spectra help differentiate them. RR Lyrae stars pulsate through the same mechanism as Cepheids, but have lower masses and luminosities. They populate the horizontal branch of globular clusters and the galactic halo. Their periods range from a few hours to a day. Unlike Cepheids, RR Lyrae stars have roughly uniform luminosities, making them useful standard candles for measuring distances to globular clusters and nearby galaxies. Long-period variables like Mira variables undergo large amplitude pulsations with periods of months to years. These are evolved red giants with extended atmospheres where molecules form and dissociate as the star pulsates. The temperature variations cause substantial changes in visible brightness because molecular opacity is temperature sensitive. Many mirror variables are thermally pulsing asymptotic giant branch stars with helium shell flashes contributing to variability. Semi-regular variables show less regular pulsations. Multiple pulsation modes may operate simultaneously, creating complex beating patterns. Convection in the extended envelopes introduces irregularities. Betelgeuse, the red supergiant in Orion, exhibits semi-regular variations with multiple periods overlaid on longer-term changes possibly related to convective cell patterns. Delta Scuti stars and Gamma Doradus stars pulsate at the intersection of the main sequence and post-main sequence evolution. Delta Scuti stars show short periods of a few hours driven by the Kappa mechanism. Gamma Doradus stars have longer periods driven by convection at the boundary between the convective envelope and radiative core. Some stars show both types of pulsation, providing rich asteroseismic data. The study of stellar pulsations connects to fundamental physics. Pulsation frequencies depend on the speed of sound waves propagating through the star, which depends on temperature, density, and composition. By measuring many pulsation modes, astronomers probe the internal structure and test models of stellar interiors. Solar-like oscillations occur in many stars similar to the Sun. These are stochastically excited by turbulent convection, producing a forest of modes with periods of minutes. Space-based missions like Kepler and TESS detect these oscillations in thousands of stars. The data constrains stellar masses, radii, and ages with unprecedented precision, revolutionizing our understanding of stellar populations and exoplanet host stars. Not all objects that form in molecular clouds become stars. If the mass is below about 8% of a solar mass, the core never gets hot enough for sustained hydrogen fusion. These objects are called brown dwarfs. Brown dwarfs are intermediate between planets and stars. They form like stars from the collapse of gas in a molecular cloud, but they don't achieve stable hydrogen burning. They do fuse deuterium briefly, and the more massive brown dwarfs can fuse lithium. But these reactions don't last long. Without a sustained energy source, brown dwarfs contract and cool over time. They start relatively hot and luminous, but fade steadily. After a few billion years, a brown dwarf becomes very faint and cool, emitting most of its light at infrared wavelengths. The boundary between the least massive stars and the most massive brown dwarfs is around 8% of a solar mass. Stars above this mass can sustain hydrogen fusion and remain on the main sequence for trillions of years. Objects below this mass cannot, and are classified as brown dwarfs. Brown dwarfs can be quite massive compared to planets. The most massive brown dwarfs approach 8% of a solar mass, which is about 80 times the mass of Jupiter. The least massive are comparable to large planets, around 10 times Jupiter's mass, though the distinction between a brown dwarf and a planet at the low mass end is somewhat ambiguous. One distinction is based on formation mechanism. Objects that form from the collapse of a cloud fragment are considered brown dwarfs, while objects that form in a protoplanetary disk around a star are considered planets. However, this distinction can be difficult to apply observationally. Brown dwarfs have been discovered in large numbers since the mid-1990s. Infrared surveys have been particularly successful because brown dwarfs are brightest at these wavelengths. Thousands of brown dwarfs are now known, and they appear to be common. possibly as numerous as stars. Brown dwarfs exhibit a variety of spectral features. The coolest have atmospheres with complex chemistry, including water vapor, methane, and even ammonia. Dust clouds form in the atmospheres of some brown dwarfs, causing variability as the clouds move across the surface with the object's rotation. The study of brown dwarfs informs our understanding of both low-mass stars and giant planets. They bridge the gap between these two regimes, exhibiting characteristics of each. The atmospheric physics of brown dwarfs is similar to that of giant planets, while their formation and early evolution resemble that of stars. Some brown dwarfs are found in binary systems, either with other brown dwarfs or with stars. The dynamics and evolution of these systems can differ from stellar binaries because the objects are less massive and their properties change significantly over time as they cool. Brown dwarfs can also have planets. Several brown dwarfs have been found to have disks, suggesting planet formation can occur around them. Detecting planets around brown dwarfs is challenging due to the faintness of both objects, but a few candidates have been identified. Substellar objects, a term that includes both brown dwarfs and free-floating planets, represent a significant population in the galaxy. They contribute to the overall mass budget and to the diversity of objects in the universe. Understanding their properties and origins is an ongoing area of research. The final states of stars, white dwarfs, neutron stars, and black holes, represent endpoints of stellar evolution. These objects no longer generate energy through fusion and gradually fade from view, but they persist for timescales far exceeding the current age of the universe. White dwarfs cool over tens of billions of years. As they radiate away their stored thermal energy, they dim and redden, eventually becoming black dwarfs. No black dwarfs exist yet because the universe is too young. But in the distant future, they will be the dominant form of stellar remnant. The cooling of white dwarfs follows predictable patterns that depend on their mass and composition. Observations of white dwarf cooling sequences in star clusters provide age estimates for the clusters. The coolest white dwarfs in a cluster set a lower limit on the cluster's age because they have had time to cool from their initial hot state. Neutron stars also cool, though more slowly than the white dwarfs initially, because their surfaces are smaller and their internal structure is more complex. Newly formed neutron stars are extremely hot, with core temperatures exceeding 1 billion Kelvin. They cool primarily through neutrino emission in the first few thousand years, then by photon emission from the surface. After 1 million years, a neutron star's surface temperature drops below a few 100,000 Kelvin, and its luminosity becomes very low. Isolated neutron stars become difficult to detect. Most known neutron stars are either pulsars, observable through their radio emission, or members of X-ray binaries, visible due to accretion. Black holes do not cool in the conventional sense. They have no surface from which to radiate, and their temperature in the classical sense is absolute zero. However, quantum mechanics introduces Hawking radiation, a process by which black holes emit thermal radiation due to quantum effects at the event horizon. The temperature of a black hole due to Hawking radiation is inversely proportional to its mass. Stellar mass black holes have temperatures of about 1 billionth of a Kelvin, far colder than the cosmic microwave background. They actually gain mass by absorbing radiation from the background, growing rather than shrinking. Only when the universe has expanded and cooled enough that the cosmic microwave background temperature drops below the black hole's Hawking temperature will black holes begin to evaporate. For stellar mass black holes, this will occur in the far future, after the universe has expanded and cooled for trillions of years. The evaporation time for a stellar mass black hole is extraordinarily long, around 10 to the 67th power years. This is so far into the future that it exceeds most other timescales in cosmology. By the time black holes begin to evaporate in significant numbers, the universe will be cold, dark, and empty of stars. Speculating about the ultimate fate of the universe involves considerable uncertainty. If the universe continues to expand at an accelerating rate, as current observations suggest, it will grow ever larger and colder. The stars will all die, their remnants will cool, and eventually even protons may decay if current theories about their stability are wrong. In such a far future, the dominant objects might be black holes, slowly evaporating through Hawking radiation. When a black hole finally evaporates completely, it releases a burst of energy, but by then, the universe will be so large and empty that such events will be isolated and insignificant. Alternatively, if dark energy behaves differently than currently assumed, the universe's expansion could decelerate, halt, and reverse. A big crunch could occur, with the universe collapsing back to a singularity. The fate of stellar remnants in such a scenario is speculative and depends on the details of the collapse. Another possibility is that the universe's expansion could accelerate to the point where a big rip occurs, tearing apart all structures, from galaxy clusters down to atoms. Such a scenario would end all stellar remnants before they could cool or evaporate naturally. These scenarios are speculative. The far future of the universe depends on the nature of dark energy, the stability of matter, and aspects of physics that are not yet well understood. What we can say with confidence is that stars, as we know them, have finite lifespans, and the universe will eventually reach a state where star formation has ceased. The era of stars represents a finite chapter in the history of the universe. It began a few 100 million years after the Big Bang, when the first stars formed, and it will end trillions of years in the future, when the last stars fade. We exist during a time when the universe is populated by stars, a brief and luminous epoch in the cosmic timeline. Stellar evolution is not just the story of individual stars. It is a story of matter transforming through nuclear processes, enriching the interstellar medium, and enabling the formation of new generations of stars and planets. This cycle connects stars to the larger structure and history of the universe. The matter in the universe began as hydrogen and helium, formed in the first few minutes after the Big Bang. For several 100 million years, the universe contained only these light elements and trace amounts of lithium. The first stars formed from this primordial gas. Those first stars were massive and short-lived. They fused hydrogen into helium, helium into carbon and oxygen, and in their cores produced elements up to iron. When they exploded as supernovae, they scattered these new elements into space. The enriched gas mixed with pristine gas and collapsed to form the next generation of stars. These stars incorporated the heavy elements, and their planets formed from material that included carbon, oxygen, silicon, and iron. Over billions of years, successive generations of stars continued this enrichment. The Sun is a third-generation star, or later, formed from gas that had been processed through multiple stellar cycles. The solar system's planets, including Earth, are composed of material synthesized in earlier stars. The iron in Earth's core, the oxygen in the atmosphere, the silicon in the rocks, all were made in stars. Life depends on this enrichment. Carbon-based life requires carbon, obviously, but also oxygen, nitrogen, phosphorus, sulfur, and many other elements. These are available only because stars produce them and supernovae disperse them. Water, essential to life as we know it, is composed of hydrogen and oxygen, the latter from stars. The story of stellar evolution is thus intimately connected to the story of life. Without stars, there would be no heavy elements, no rocky planets, no water, no organic molecules. The universe would remain a sea of hydrogen and helium, incapable of supporting complexity. This perspective places stars at the center of the cosmic narrative. They are not merely objects in the sky. They are furnaces that create the elements, engines that process matter and energy, and ultimately, the reason the universe is capable of supporting life and structure. The cycle is ongoing. Stars are forming now, in regions like the Orion Nebula and other molecular clouds. Massive stars are exploding, enriching the interstellar medium with fresh, heavy elements. The next generation of stars and planets is being built from this enriched material. In our galaxy, star formation continues at a rate of about 1 to 2 solar masses per year. This may seem slow, but over billions of years, it represents the birth of billions of stars. Each one follows the path determined by its mass, contributing to the cycle in its own way. Low-mass stars contribute gradually, living long lives and eventually returning enriched material through planetary nebulae. Massive stars contribute explosively, living briefly and ending in supernovae that pump energy and heavy elements into the interstellar medium. Both types play essential roles. The interstellar medium itself is a dynamic environment. It consists of gas in various states, cold molecular clouds, warm neutral regions, hot ionized bubbles, all interacting and exchanging material. Supernova shock waves compress clouds, triggering new star formation. Stellar winds and radiation disperse clouds, enriching and heating the gas. Galactic dynamics also play a role. Spiral density waves in disk galaxies compress gas as it passes through, promoting cloud formation and star formation. The gas orbits the galactic center, cycling in and out of spiral arms, alternately compressed and relaxed. On larger scales, galaxies themselves interact. Collisions and mergers between galaxies can trigger bursts of star formation as gas clouds collide and compress. The history of star formation in the universe is tied to the history of galaxy formation and evolution. Star formation was more vigorous in the past. The rate of star formation in the universe peaked several billion years ago and has been declining since. As the universe expands and galaxies exhaust their gas supplies, fewer new stars form. The rate will continue to decline, and eventually, star formation will cease. When the last star forms and the last massive star explodes, the era of active stellar evolution will end. The remaining low-mass stars will continue to burn for trillions of years, but no new stars will replace those that die. The universe will gradually dim as stars exhaust their fuel and cool. This distant future is not something we will experience, but it provides context for our place in time. We live during the stelliferous era, the epoch when stars light the universe. This era is finite, bounded by the end of the Dark Ages at one end and the eventual cessation of star formation at the other. Recognizing this temporal context adds depth to our understanding. Stars are transient, at least on cosmological timescales. They have beginnings and endings. The universe is not eternal in its current form. It evolves, and the structures we see, galaxies full of stars, are temporary features of a particular epoch. Yet within that temporariness, there is profound richness. The variety of stellar types, the complexity of their evolution, the intricate cycles of matter and energy. All of this emerges from the interplay of gravity, nuclear physics, thermodynamics, and quantum mechanics. Stars are laboratories, where these fundamental forces shape matter under extreme conditions. Studying stars is a way of studying the universe itself. The principles that govern stellar structure and evolution are universal. They apply to stars in distant galaxies, in different epochs, in environments unlike our own. The life cycle of a star is a window into the workings of the cosmos. Understanding stellar evolution requires observation. We cannot watch a single star evolve because the timescales are too long. Instead, we observe many stars at different evolutionary stages and piece together the sequence. The Hertzsprung-Russell diagram is a fundamental tool in this effort. It plots stars according to their luminosity and surface temperature. Stars group into distinct regions on this diagram, and these regions correspond to different evolutionary stages. The main sequence is a diagonal band where stars spend most of their lives. The position on the main sequence depends on mass. Hot, luminous stars are at the upper left. Cool, dim stars are at the lower right. Our Sun sits in the middle. Red giants and supergiants occupy the upper right of the diagram, where stars are luminous but cool. White dwarfs are at the lower left, faint but hot. The paths that stars follow on this diagram as they evolve are called evolutionary tracks, and they depend on the star's mass. By observing star clusters, we can see snapshots of stellar evolution. All stars in a cluster formed at roughly the same time from the same cloud of gas. They have the same age and initial composition, but different masses. This allows us to see how mass affects evolution. In a young cluster, the main sequence is fully populated. Massive stars are still on the main sequence, along with less massive stars. The cluster is bright and blue because the massive stars dominate the light. In an older cluster, the most massive stars have already evolved off the main sequence. They have become red giants or have exploded as supernovae. The main sequence ends at some intermediate mass, called the main sequence turnoff. Stars more massive than this have evolved further. The position of the turnoff depends on the cluster's age. In very old clusters, only low-mass stars remain on the main sequence. In younger clusters, more massive stars are still there. By identifying the turnoff mass and using models of stellar evolution, we can estimate the cluster's age. Globular clusters are among the oldest objects in the galaxy, with ages of around 10 to 13 billion years. Their main sequence turnoff is at masses slightly below the Sun's mass. They contain large populations of red giants, and their horizontal branch is well populated with stars burning helium in their cores. Open clusters are younger, with ages from a few million to a few billion years. They show a variety of evolutionary stages depending on their age. Young open clusters contain massive main sequence stars, pre-main sequence stars, and sometimes protostars still embedded in their natal clouds. Older open clusters have evolved red giants and may contain white dwarfs. Spectroscopy is another critical tool. By analyzing the light from stars, we can determine their composition, temperature, surface gravity, and motion. Spectral lines reveal the presence of specific elements and their ionization states, which depend on temperature. Different types of stars have characteristic spectra. O and B stars, the hottest, show lines of ionized helium and metals. A stars show strong hydrogen lines. F and G stars, like the Sun, show lines of ionized metals. K and M stars, the coolest, show molecular bands. The width of spectral lines provides information about rotation, turbulence, and surface gravity. Doppler shifts indicate the star's motion toward or away from us. In binaries, the periodic shifts of the lines reveal the orbital motion and allow us to determine masses. Photometry, measuring the brightness of stars at different wavelengths, provides information about temperature and luminosity. Multiband photometry can distinguish between stars of different types and identify unusual objects like brown dwarfs, white dwarfs, or variable stars. Modern surveys observe millions of stars repeatedly, building up light curves that reveal variability. Time-domain astronomy has discovered transients like supernovae, novae, and tidal disruption events. Large datasets enable statistical studies of stellar populations. Space-based telescopes have been transformative. Hubble has imaged nebulae and star-forming regions in exquisite detail, revealing protostars, protoplanetary disks, and the structure of planetary nebulae. Chandra and XMM Newton have observed X-ray binaries, supernova remnants, and the hot gas in stellar coronae. Infrared telescopes like Spitzer and the James Webb Space Telescope peer through dust to see embedded protostars and brown dwarfs. They detect the thermal emission from disks and can characterize the atmospheres of exoplanets orbiting other stars. Gravitational wave detectors like LIGO and Virgo have opened a new window. They detect the mergers of compact harsh objects, neutron stars and black holes, confirming predictions and revealing populations of black holes in unexpected mass ranges. Theoretical models complement observations. Stellar evolution codes solve the equations of stellar structure numerically, tracking how stars change over time. These models predict luminosities, temperatures, lifetimes, and final states. Comparing model predictions to observations tests our understanding of the physics. Uncertainties remain. Mass loss rates, convection, rotation, magnetic fields, all influence evolution, and our treatment of these processes is approximate. Binary interactions add complexity. The formation of massive stars and the details of supernova explosions are not fully understood. Despite these challenges, our picture of stellar evolution is robust. The main features, the sequence from protostar to main sequence to giant to remnant, are well established. The timescales, the dependence on mass, the products of nucleosynthesis, all are constrained by observations and agree with models. The study of stellar evolution continues to advance. New observations challenge models and refine our understanding. Discoveries of unusual objects push the boundaries of what we thought possible. The field remains vibrant and full of questions. The discovery of planets around other stars has transformed our understanding of stellar systems. Exoplanets orbit stars at various evolutionary stages, from young pre-main sequence stars to white dwarfs, revealing the diversity of planetary systems and the connections between stellar and planetary evolution. Planets form in protoplanetary disks around young stars. These disks consist of gas and dust left over from star formation. Over millions of years, dust grains stick together, forming larger particles, then planetesimals, and eventually planets. The process is complex and depends on the properties of the disk and the star. Temperature gradients in the disk determine which materials can condense. Close to the star, only metals and silicates remain solid, forming rocky planets. Farther out, beyond the ice line, water and other volatiles condense. allowing the formation of icy cores that can grow massive enough to capture gas and become giant planets. The composition of the disk depends on the star's metallicity. Stars with higher metallicities have disks enriched in heavy elements, which may facilitate planet formation. Observations confirm that giant planets are more common around metal-rich stars, supporting this idea. Planets can migrate after they form. Interactions with the disk or with other planets can cause a planet's orbit to change. Some giant planets migrate inward, becoming hot Jupiters orbiting close to their stars. Other planets may be ejected entirely, becoming free-floating planets wandering through space. The star's evolution affects its planets. As a star becomes a red giant, it expands and may engulf inner planets. The outer planets receive more energy, and the habitable zone shifts outward. Moons of giant planets in the original habitable zone might become habitable as the star swells. When the star sheds its envelope to become a white dwarf, the dynamics change again. Planets may be scattered by asymmetric mass loss. Tidal interactions with the expanding star can alter orbits. Some planets may survive, orbiting the white dwarf in stable configurations. Observations have confirmed planets around white dwarfs. Metal lines in white dwarf spectra often indicate accretion of rocky material, possibly from disrupted asteroids or planets. Some white dwarfs show infrared excess from dusty disks, remnants of shattered planetary systems. Planets also exist around pulsars. The first confirmed exoplanets were found around a millisecond pulsar. These planets likely formed from the debris of a supernova or from material accreted during the pulsar's spin-up phase. The environment is harsh, bathed in radiation from the pulsar. The habitability of planets depends on the star's properties. Stars like the Sun provide stable energy output over billions of years, giving lifetime to evolve. More massive stars burn out too quickly. Less massive stars are long-lived, but emit less energy, placing the habitable zone closer in. Red dwarfs, the most common stars, have habitable zones close to the star. Planets there may be tidally locked, always facing the star with one side. The star's flares and strong magnetic activity pose challenges for habitability. However, red dwarfs are abundant and long-lived, offering many potential habitats. The study of exoplanets informs stellar evolution in subtle ways. Planets can affect the star's rotation through tidal interactions. They may influence magnetic activity. In rare cases, planets could even alter the star's evolution by accreting onto it or by affecting the star's angular momentum. Conversely, stellar evolution models help interpret exoplanet observations. Understanding the star's age, luminosity, and spectral type is essential for characterizing its planets. Stellar activity complicates planet detection and characterization, requiring careful modeling. The connection between stars and planets is fundamental. Stars create the conditions for planets to form, provide the energy that drives planetary climates, and determine the long-term fate of planetary systems. Studying one requires understanding the other. The history of star formation in the universe is tied to the broader history of cosmic evolution. The first stars formed a few 100 million years after the Big Bang, in an era called cosmic dawn. These population 3 stars formed from pristine gas and were likely very massive. Their formation triggered reionization, the process by which ultraviolet radiation from stars ionized the neutral hydrogen that filled the early universe. This changed the thermal state of the gas and affected subsequent star formation. Reionization was complete by about 1 billion years after the Big Bang, As galaxies assembled, star formation increased. Small galaxies merged to form larger ones, and gas funneled into the centers, fueling bursts of star formation. The rate of star formation in the universe peaked around 10 billion years ago, a few billion years after the Big Bang. Since that peak, the star formation rate has declined. Galaxies have consumed much of their gas. Feedback from supernovae, an active galactic nuclei heats and expels gas, reducing the supply available for forming new stars. The expansion of the universe also plays a role, as it becomes harder for gas to cool and collapse in the lower density environment. The decline continues today. Current star formation rates are about 10 times lower than at the peak. In the future, rates will drop further. Eventually, star formation will cease altogether, as gas supplies are exhausted or dispersed beyond the reach of galaxies. Different types of galaxies have different star formation histories. Spiral galaxies, like the Milky Way, have ongoing star formation in their disks. Elliptical galaxies are dominated by old red stars and have little ongoing star formation. The reasons involve both the gas content and the dynamics of the galaxy. Interactions and mergers between galaxies can trigger starbursts, brief periods of intense star formation. Gas clouds collide and compress, leading to rapid formation of massive stars. Starburst galaxies can form stars at rates hundreds of times higher than normal, but the episodes are short-lived, lasting only tens of millions of years. Studying galaxies at different distances allows us to see different epochs. Because light travels at a finite speed, looking at distant galaxies shows us the universe as it was in the past. High redshift galaxies appear as they were billions of years ago, providing a window into earlier cosmic times. The James Webb Space Telescope has observed galaxies as they were just a few 100 million years after the Big Bang. These early galaxies were smaller and less structured than modern galaxies. Their stellar populations were young, and star formation was vigorous. The observations test models of galaxy formation and stellar evolution in the early universe. Cosmic chemical evolution is evident in the changing metallicity of galaxies over time. Early galaxies had low metallicities, reflecting the limited enrichment by the first stars. As star formation continued, metallicity increased. Modern galaxies have much higher metallicities, with variations depending on the galaxy's history. The buildup of metals affects subsequent star formation. Higher metallicity gas cools more efficiently, potentially fragmenting into lower mass stars. It also affects dust content, which plays a role in cooling and in the formation of molecules. The relationship between metallicity and star formation is complex and still being studied. Galactic archaeology uses the chemical composition of stars in the Milky Way to infer its history. Stars preserve a record of the composition of the gas from which they formed. By measuring abundances of many elements, astronomers can trace the contributions of different sources: supernovae of various types, asymptotic giant branch stars, neutron star mergers. The most metal-poor stars in the Milky Way's halo provide clues about the earliest generations of stars. These stars formed from gas, enriched by only a few supernovae, perhaps even a single supernova. Their abundance patterns differ from stars that formed later, offering insights into the first stellar explosions. The study of stellar populations links stellar evolution to cosmology. Stars are not isolated from the larger universe. They are products of cosmic evolution, shaped by the conditions in which they form. Their lives and deaths, in turn, shape the evolution of galaxies and the universe. The life cycle of stars is a process that spans timescales beyond human comprehension. From the slow collapse of molecular clouds to the billions of years a star spends on the main sequence, to the gradual cooling of white dwarfs over trillions of years, stellar evolution operates on a scale that dwarfs individual human experience. Yet this immense temporal span connects directly to our existence. The atoms in our bodies were forged in stellar cores and dispersed by stellar explosions. The energy that powers life on Earth comes from a star in the middle of its main sequence lifetime. Our planet formed from material enriched by generations of earlier stars. We live during a particular moment in cosmic history, the stelliferous era, when stars light the universe. This moment will not last forever, but while it does, stars continue their cycles, forming from clouds, fusing elements, enriching the interstellar medium, and leaving behind remnants that persist into the distant future. Understanding these cycles gives us perspective. We are part of a vast and ancient process, a thread in the tapestry of cosmic evolution. The same forces that govern the birth and death of stars have shaped the matter that composes us. There is a certain comfort in this continuity. Stars have been forming, living and dying for billions of years before us, and will continue for billions of years after. The cycles are robust, driven by fundamental physics, operating across the universe wherever matter and gravity and nuclear forces interact. The future of stellar evolution research holds exciting prospects. Gravitational wave astronomy will reveal populations of merging compact objects throughout cosmic history, constraining formation channels and evolution pathways. Multi-messenger observations combining gravitational waves, electromagnetic radiation, and potentially neutrinos will provide comprehensive views of the most energetic stellar events. Advanced simulations incorporating increasingly realistic physics will improve our models of complex processes like supernova explosions, common envelope evolution, and mass transfer in binaries. Exascale computing enables three-dimensional models following evolution over long timescales, capturing instabilities and asymmetries that simpler models miss. Large surveys will catalogue billions of stars, mapping the galaxy's structure and history in unprecedented detail. Machine learning algorithms will identify rare objects and unusual evolutionary states. The combination of photometry, spectroscopy, and astrometry will enable population studies constraining galaxy formation and chemical evolution models. The search for the first stars continues. Next-generation telescopes may detect individual population 3 stars in the early universe, or infer their properties from their descendants. Understanding these first stars illuminates cosmic dawn and the beginning of chemical enrichment. Each discovery reveals new complexities while answering long-standing questions. Stellar evolution remains a vibrant field connecting nuclear physics, hydrodynamics, gravitational physics, and observational astronomy in the quest to understand how stars are born, live, and die. The universe is not static. It changes, evolves, becomes more complex. Stars are agents of that change, processing hydrogen into heavier elements, organizing matter into structures, seeding the cosmos with the raw materials for planets and life. In studying stars, we study ourselves. We learn where we came from, how the elements that make up our world were created, and how the conditions for life arose. The journey from nebula to supernova is also the journey that made our existence possible. The story of stars is the story of transformation. Gravity shapes matter, nuclear forces rearrange nuclei, thermodynamics drives energy flows. From these basic ingredients emerges the full diversity of stellar phenomena. the rich tapestry of stellar types and evolutionary paths. We observe stars in their various stages, piecing together the sequence from the light they emit and the patterns they form. We model their interiors, using physics to predict how they change. We test those predictions against observations, refining our understanding. The work continues. New discoveries challenge assumptions. Unusual objects defy easy classification. The boundaries of knowledge expand, but the fundamental picture remains. Stars are born, live, and die, transforming matter and energy in ways that shape the cosmos. As you rest tonight, consider that the cycles continue. Stars are forming in nebulae, fusing hydrogen in their cores, swelling into giants, exploding as supernovae. The processes that have operated for billions of years proceed now, at this moment, across the galaxy and beyond. The universe is vast, but it operates according to principles we can understand. Stars, for all their diversity, follow paths determined by mass, composition, and the laws of physics. Their stories are written in light, waiting to be read by those who look up and wonder. And so we reach the end of this exploration. The life cycle of stars, from nebulae to supernovae, from protostars to white dwarfs, from massive stars to neutron stars and black holes. The cycle of matter, transforming and enriching, enabling complexity and structure. Rest well, knowing that the cosmos continues its ancient rhythms, that stars shine and fade, that matter is endlessly recycled, and that the cycles that made our existence possible unfold across the vastness of space and time.